flow, and hence the convective heating rate that is produced in the channel shroud. The operational functions of the combustor are provided by the combined controller and programmer console. Flow metering systems, control valves, and combustor safety interlock sensor signals are integrated through the console, resulting in near automatic operation. The console provides continuous control of the gas flow rates by function generator input to the control loop. The control program is designed to establish a convective heating variable with time so that the panel surface temperatures respond to produce the temperature profile. Each thermal protection system configuration was cycled through a predicted entry profile. The duration of the series was 20 cycles, which represents the equivalent of 100 missions as determined experimentally. The profile consists of a rise in ambient temperature to 2400 degrees Fahrenheit in 300 seconds, a 600-second hold at 2400 degrees, a gradual decrease to 1600 degrees in 1000 seconds, followed by a hold for 400 seconds, and then a rapid decrease in flow until system shutoff at 2500 seconds and the introduction of gaseous nitrogen for cooling to ambient conditions. The specimen with its copper holding fixture is installed on guide channels and slid into the chamber. After instrumentation attachment and all pretest data and control system calibrations have been accomplished, the combustor gas supply systems are pressurized. The facility temperature and pressure safety interlocks are activated to go status. Facility and instrumentation cooling water and airflows are started, and the automatic ignition sequence is begun with a gaseous nitrogen purge through the combustor gas supply system. The spark ignition switch is depressed, and the pilot is automatically ignited at the completion of the purge cycle. The oxygen flow rate is automatically started at the initial test heating level during the pilot ignition sequence. A flame detector circuit senses the pilot flame and causes the pilot indicator light to illuminate. This permits the next combustor ignition sequence to function. The combustor start switch is depressed, opening the main hydrogen gas flow control valve at the initial heating level flow rate. The control sequencer shuts down the pilot flame after a preset time interval, and the flame detector senses combustor flame. An automatic shutdown and purge sequence will begin if the flame detector or other facility safety interlock devices sense that combustor operating characteristics are not within defined limits during the specimen heating cycle. The flow program charts are started immediately and checked for synchronization. The specimen temperature data system is spot checked after the heating cycle is started. The data from each thermocouple channel is recorded in digital form on a Dymex system paper punch tape and printer once every 10 seconds. Selected thermocouple channels are continuously recorded and monitored by the test conductor throughout the heating cycle. The combustion gas flow rates are displayed on the console indicator panel. Observation of the programmer chart tracking, flow rates, and specimen temperature are conducted throughout the heating cycle. The surface of the specimen can be observed during the entire profile, with especially good illumination occurring during the highest heat intensities. It can be seen that the T-stiffened heat shield does not perceptibly distort, nor do the protuberances of the retainers create a flow interference or distortion problem. The leakage effects around the longitudinal retainers appears to be minimal, and the insulation was undisturbed by any internal flow. Temperature distribution was uniform over the panel surface, and the thermal lag throughout the depth of the system was as predicted. The open corrugation specimen also performed well, although greater flow disturbances and surface temperature distributions were observed. The specimen was designed to absorb thermal deflections by elongating the curvature of the corrugations. The corrugation deflections were within the predicted limits, and all surfaces were free of substrate oxidation. Upon completion of the heating profile, the combustion shutdown and post-test purge sequence is accomplished by the test conductor actuating the manual shut-off switch. Post-test purge is performed for 2 minutes while the facility cooling and gas pressurization systems are shut down. The purge is stopped and data recording continued until specimen temperatures recover to near ambient conditions. A visual examination of the panel surface is conducted between heating cycles after the temporary removal of the specimen housing assembly from the shroud. Surface conditions are easily photographed between test cycles for visual records of panel performance. Following the 20-cycle exposure, each specimen was disassembled and examined for structural changes and substrate erosion. All plugs and bolts were readily removed by applying 25 to 30% more torque than was used when installing the fasteners. All plugs and bolts were found to be in excellent condition, with no evidence of gross oxidation or incompatibility between the two dissimilar metals. The heat shields and the retainers also exhibited no evidence of oxygen contamination or structural degradation. Conclusions based on the hot gas flow tests and similar radiant heat lamp tests determined that both metallic radiative thermal protection systems employing silicide-coated columbium alloy and TD nichrome components were capable of sustaining 100 missions, and indeed offer a viable system for protecting the space shuttle from the high temperatures of atmospheric entry.